This video is about a very appealing and very important idea in computer science, that of pipelining. The idea is not restricted to computer science, it's a very natural one and finds application in a variety of settings. But as we are going to see, microprocessor design has used this idea to its fullest possible extent by formalizing the idea. Let us first start with some fun videos though. These videos are available on YouTube. The first two are Charlie Chaplin's critique of industrialization, the use of human workers in the industry's assembly line or pipeline. The third one is also similar. While you enjoy the videos, also make sure that you pay specific attention to the pipeline or the assembly line and how it behaves. We learn the following lessons by watching those videos. First is that pipelining is a natural idea, at least for machines. Human beings too are good at doing repetitive tasks, but beyond a certain point, it affects their human nature. That is what Charlie Chaplin is critiquing. But the lesson we take forward is that pipelining is good for machines. The next lesson we learn is that the overall speed is only as good as the slowest unit in the assembly line. And any non-uniformity is bad for the pipeline, and exceptions are really bad. You must have seen the exception in the Charlie Chaplin video in the form of Chaplin's spanner getting stuck and his co-worker hitting him on the hand and the pipeline had to be stopped and so on. What we are going to do going forward is to formalize the notion of pipeline and see how we can use it in microprocessor design. First, let us take an example which is closer to Charlie Chaplin's assembly line but formalizes things a bit more. Let us take this example of bicycle manufacture. Let us say the first step involved here is to make the frame of the bicycle, and then the frame has to be painted, and then we fit the wheels, and after fitting the wheels we fit the accessories as the final step. This is a simplified assembly line for the manufacture of a bicycle to illustrate the notion of pipelining and what happens when we employ pipelining. Let us say for the purpose of illustration that the first two steps take 1 hour each, the third step takes 2 hours, and the fourth step also takes 1 hour. In this scenario, how much time will it take to make one bicycle? And how much time will it take to make, let's say, 10 bicycles? For the case of making 10 bicycles, I need to tell you whether we are going to use pipelining or no pipelining. First, let us answer the scenario of how much time it will take to make 10 bicycles without pipelining. Next, answer the question of how much time it will take to make 10 bicycles with pipelining. In this case, we are going to assume that there is a separate human or a separate machine for each of these steps. So for making the frame, there is a separate machine, and for painting the frame, there is a separate machine or human, and for fitting the wheels, there is a separate unit, and for fitting accessories, there's a separate unit. So these 4 units can potentially be operated in parallel in a pipeline fashion. In this scenario, how much time is it going to take? In pipelining, we realize that we are going to have the second bicycle enter the pipeline when the first bicycle has moved from the first unit of work to the second unit of work. Likewise, when the first unit of work moves to the third step, the second unit will move to the second step and the third unit of work will move to the first step, and this will continue. We can represent this in the form of a pipeline timing diagram. The first bicycle enters the pipeline first, and when it moves to the second step, I have represented the second step here with a different color, and the third step with another different color, and the fourth step with yet another different color. As you can see, second bicycle will enter the first step when the first bicycle has moved on to the second step. Likewise, when the first bicycle has moved on to the third step, the second bicycle enters the second step and the third bicycle will enter the pipeline in its first step. And then we have something happening. Since the third step takes 2 hours to complete, the first bicycle is in the third step at this point. The second bicycle will complete its second step within 1 hour of its entry into the second step, and then it has to wait. Likewise, the third bicycle also has to wait in the first step until such point as it can move to the second step. which will happen when the first bicycle has moved on to the fourth step, and then the second bicycle will then move to the third step, third bicycle will move to the second step, and the fourth bicycle will then enter the pipeline. Similar delay will happen before bicycle 3 can enter its third step. Likewise, before bicycle 4 can enter its second step. During these idle periods, which are caused due to non-uniformity in the time taken in the various steps, we see that only the slowest unit is working in this particular example. In this pipeline timing diagram, can you tell what the y-axis represents? And what does the x-axis represent? The y-axis represents in the downward direction different units of work which enter and exit the pipeline, and the x-axis represents time. So pipelining in abstract is nothing but breakdown of work that must be done into various stages. In this example, again, I have broken down into 4 different stages represented by 4 different colors, and there are different units of work which must go through all 4 stages to complete the work. First, one unit of work enters stage 1. When it moves on to stage 2, the second unit of work represented by W2 here enters stage 1, and this proceeds. When W1 goes to stage 3, W2 enters stage 2, and W3 enters the pipeline in stage 1, and so on. In this diagram, can you tell what is the y-axis? This diagram is nothing but the earlier pipelining diagram drawn differently. Here, time grows downwards along the y-axis. Here is a thought exercise for you. What other examples of pipelining can you think of from real life? Here are some examples I could think of. Water pipeline is a pipeline. Of course, this is the origin of the word pipeline itself. Here, different abstract portions of the water move through different abstract stages of the water pipeline. Another very interesting example of pipelining is that of network packets. Let's say you have a network in which client C is connected to server S via 2 routers, and packets are coming from server to the client. In that case, the first packet enters the pipeline here. When the first packet is going from router R1 to router R2 towards C, the second packet has already entered the pipeline traveling from S to R1. Likewise, when the first packet is traveling from R2 to C, the second packet is traversing from R1 to R2, and the third packet has entered the pipeline, roughly speaking. So the internet is full of instances of pipelining. I have also put to use this idea of pipelining in my course project evaluation. In a course, I had a heavy project and I wanted to evaluate paying due attention to different parts, while at the same time finishing the evaluation within reasonable period of time. So here is what I did. I had 8 different TAs sitting at 8 different desks, and each student coming for evaluation will move from one TA to another, and each TA evaluates one portion of the project. Well, in this scheme of things, what do you think are the advantages over the alternative where, let us say, I divide the set of students into 8 different groups, and the first group goes to the first TA, the second group goes to the second TA, and so on. That is an alternate scheme of parallelism. What do you think are the advantages of pipelining versus this alternate mode of parallelism? And what do you think are the disadvantages? Well, I found this pipeline model much better because it allowed me to have one TA correct each portion of the project for all of the students, and that gave a little bit of uniformity. Not only that, in this pipeline model, each TA had to focus on only one aspect of the project and hence did not need to know about all of the aspects of the project. Well, of course, the disadvantage with pipelining as opposed to parallelism through the alternate means is that if one of the stages of correction had more work involved, then that would involve unnecessary pipeline delays and also handling of exceptions like we saw in the Charlie Chaplin video. There are of course many other examples of pipelining you can think of, because pipelining is a natural idea. Well, pipelining allows for a natural form of parallelism, and let us now analyze what speedup is possible using pipelining. Let us continue with the bicycle manufacture example where there were 4 stages. The first 2 stages taking 1 hour each, the third stage taking 2 hours and the fourth stage also taking 1 hour. In this case, let us find out what is the time taken to manufacture n bicycles. First, what is the time taken to manufacture n bicycles without using pipelining? Well, without using any parallelism, we are going to have 5n hours as the time taken to manufacture n bicycles because each bicycle takes 5 hours. With pipelining, what is the time that is going to take for manufacturing n bicycles? To analyze this, we see that the first output from the pipeline takes 5 hours to come out, and each subsequent output comes after every 2 hours. This 2 hours here corresponds to the bottleneck in the pipeline, which is the third stage in this example. So you can do the analysis and find that the speed up will be 5/2 for large n. Let us next analyze a slightly different scenario. Suppose the third stage of fitting wheels also took only 1 hour. Then what will be the speed up? The speed up in this case will be 4n divided by 4 plus n minus 1. 4 is the amount of time it takes for the first output to come out in the pipeline implementation, and after every 1 hour, every subsequent output comes. So this tends to 4 for large values of n. Let us next analyze yet another scenario where, let us say, fit wheels, the third stage, takes 2 hours but is broken down into 2 sub-steps of fit front wheel and fit rear wheel, each of 1 hour. So the pipeline now has 5 stages instead of 4. In this case, how much time is it going to take for the pipeline implementation, and what will the speed up be? Well, we see that the speed up will be 5 for large n, 5n divided by 5 plus n minus 1, which tends to 5 for large values of n. Abstracting out a bit further, we see that if a pipeline has k stages, each taking same time t, then the time taken for n units without pipeline will simply be n times kt. With pipelining, it is going to be kt. Kt is the time to set up the pipeline, or the time to first output, or the time to fill the pipeline. This first term is known by these various names. This second term represents the amount of time taken for each subsequent output. T is the time taken for each subsequent output multiplied by the remaining n minus 1 units. Now, as you can imagine, if the value of n is small compared to the value of k, then the pipeline setup time is going to be a significant component of this overall time to completion of n units of work. For large values of n, the speed up is going to tend towards k, which is nothing but the number of stages in the pipeline. So this is the ideal speed up a pipeline can achieve. A pipeline with k stages can ideally achieve a speed up factor of k. In the above statement, the word ideal is very important. There are several necessary conditions in order to achieve this ideal speed up. The first condition is that all stages must be of equal length in time. We are also going to assume that there is enough hardware or enough number of hands for each of the stages in the pipeline. For example, in our bicycle manufacture scenario, we cannot have the same spanner or same machine or same person being used for 2 different stages. Given these, can you think of why, for example, during my project evaluation in that course, I could not have achieved a speed up of a factor of 16 using 16 pipeline stages? What might be the possible reasons why I could not have done this? There are actually many more conditions which need to be satisfied to achieve this ideal pipeline speed up, as we will see later. When talking about a pipeline, it is important to distinguish between latency versus throughput. Latency is the time taken for 1 unit of work between when it enters the pipeline and when it completes the work by exiting the pipeline. This is latency from the perspective of a single unit of work. The throughput is the rate at which work completes at the end of the pipeline. In a non-pipeline implementation, throughput is proportional to 1 over latency. However, in a pipelined implementation, throughput will generally be better than 1 over latency. As we have seen in the bicycle example, the latency for 1 unit of cycle was 5 hours, but the throughput was 1 cycle exiting the pipeline every 2 hours. Let us now switch from talking about pipelining in abstract to talking about pipelining in the context of MIPS. Let us recall the MIPS multi-cycle implementation for this. The MIPS multi-cycle implementation for the instruction subset involved the following stages. The first stage was common, involving instruction fetching and PC+4 addition. The second stage involved register reading and branch target computation, and this was also common to all instructions. Stage 3 involved ALU operation for register, memory address computation also using ALU for load word and store word, branch condition computation for the branch instruction, and this also used the ALU. Stage 4 was different for memory access instructions and register instructions. For load word and store word, stage 4 involved memory access, whereas for register instructions, stage 4 involved register write back, and stage 5, which was there only for load word, involved register write back. What we need to observe here to introduce the notion of pipelining in MIPS is the commonality between all of these stages. See how stage 1 and stage 2 are of course common for all instructions. Even for stage 3, which is different, the same operation is being performed, the same unit is being used for different kinds of instructions. And if we do a slight modification by, let us say, doing nothing in stage 4 of register instructions and doing the register write back in stage 5, if we make such a modification to the execution of register instructions, then we see that all of the 5 stages are almost the same for all of the instructions. Well, why are we talking about uniformity of all of the stages for different instructions? The reason is that uniformity enables good pipelining. Variability is bad for pipelining, while uniformity is good for pipelining. While talking about pipelining in MIPS, we are going to name the 5 stages as follows. The first stage, we are going to name it IF, which stands for instruction fetch. The second stage, we are actually going to call it ID, which stands for instruction decode. Although we have said earlier that stage 2 involves register reading and branch target computation, the name we are going to give for stage 2 in the pipeline implementation of MIPS is instruction decoding, and this is because a very important thing happens in stage 2, that is the generation of various control signals which are necessary for subsequent stages of execution are going to be generated by looking at the opcode, and that is why this stage gets the name instruction decode, to signify the importance of reading the opcodes from the instruction. The third stage, which involves ALU operation for all of the instructions in our instruction subset, is going to be called EX, which stands for execute. The fourth step, assuming we are going to move the register write back of register instructions also to stage 5, is going to involve only memory operations. So we call stage 4 as mem, and stage 5, since it involves register write back, we call it WB, which stands for write back. So the names of the 5 stages are instruction fetch IF, instruction decode ID, EX execute, mem memory operation, and WB for write back. After having identified the 5 stages, we can do pipelining for MIPS potentially as follows. Let us look at a simple sequence of load word instructions, 1, 2, 3 load word instructions in this example, and these are the 5 stages of the pipeline: IF, ID, EX, mem, and write back. When the first instruction enters the second stage of the pipeline, the second instruction enters the first stage, just like in our bicycle example, and when the first instruction enters the third stage, the second instruction enters the second stage, and the third instruction enters the pipeline in the first stage. Such pipelining is potentially possible. We are going to see how it can be enabled. The uniformity of the operations in the various instructions in the various stages of the pipeline is going to allow us to do similar pipelining for any sequence of instructions. Let us look at this example, which involves two register instructions and one load word. We can have a similar pipeline like earlier, except that I have grayed out here this memory stage, which means that even though there is a mem stage for these register instructions, it is actually going to do nothing with memory. It's like, let us say in our bicycle example, somebody ordered a bicycle without any painting. So such bicycles will pass through the pipeline all the same, but the painting stage will do nothing. Just like that, for register instructions, here we do nothing in the mem stage. Well, what do you think is going to be the effect of adding this additional cycle? We have increased the number of cycles taken for register instructions from 4 to 5. What do you think the effect of this is going to be? Well, it is going to have an effect on the latency of those instructions. However, what we are concerned about in the pipeline implementation is going to be the rate at which instructions come out of the pipeline, that is the rate at which instructions finish execution. This is also called the instruction throughput. The instruction throughput is not going to be affected because we have increased the number of cycles taken for register instructions from 4 to 5. So in summary, we have seen that pipelining is a natural idea for speeding up. We break up the work to be done into various stages and use pipelining parallelism among those different stages. We have the notion of latency versus throughput. Latency is important when we have only small number of units of work to be done, but throughput is the more important metric when we have large number of units of work which must pass through the pipeline. For example, a large number of bicycles to be manufactured, or a large number of students' projects to be corrected, and so on. In the case of MIPS, we saw that the uniformity in the various stages of execution in the multi-cycle case is going to allow us to do a transformation of that multi-cycle implementation to pipeline implementation. However, such a transformation is not going to be easy. We have to deal with various kinds of issues with pipelining. These go by the name of hazards. You must also have noticed in the videos that you saw that pipelines don't like anything abnormal to happen. Even as small a thing as Charlie Chaplin wanting to scratch his arm or take a break causes a lot of pain to the pipeline. And we saw that when Charlie Chaplin went under the machine where he wasn't supposed to go, the pipeline not only stopped, but it also had to be rolled back. Well, it turns out that in the MIPS pipeline implementation as well, we need to do a lot of such things, and these are going to be very interesting and challenging.